Hello and welcome to Algebra 2. We are on lesson 1111. This is part 1. We're breaking this into 2 parts. Today's notes will be about permutations and combinations. So the first thing we're going to learn about is the fundamental counting theorem, which is using multiplication to count as a shortcut way to count. So for example, if we have 3 pairs of pants and 2 shirts, and we want to know the total number of different outfits we can wear, we'll take those 3 pairs of pants, multiply it by those 2 shirts, and we'll get 6 combinations of clothes. That's the fundamental counting theorem, and by now you've probably seen it once or twice in your math. And we can use the fundamental counting theorem in problems like this. This is problem 1, and it says how many more license plates were there in 91 than in 1918? So if we look at 1918, all right, there's 1, 2, 3, 4, 5 numbers, all numbers, and we can use the fundamental counting theorem to figure out the total amount instead of counting them all. So if we look at the first number here, right, it starts with 4, but there's 10 total numbers they can pick. That's 0 through 9. And for the second one, there's another 10, and then 10 for the third number, 10 for the fourth number, and 10 for the fifth number. So we get 10 times 10 times 10 times 10 times 10, which is a 1 with 5 zeros, or 100,000. Now obviously that wouldn't cut it in today's times, because there's more than 100,000 cars in Oregon. And in 91, the license plates looked like over here. And they had 3 letters followed by 3 numbers. So using the fundamental counting theorem again, we're going to do the same exact thing, except for instead of 10, here we're going to have 26, right? 26 letters in the alphabet times 26 times 26, and then 3 numbers, which is 10 times 10 times 10. And let's see, I'm not that good at math, so I'm going to use my calculator, just right here, and use the calculator, and I'm going to have 26 times 26 times 26 times 10 times 10 times 10. Just make sure I did that right. 3 26s and 3 10s. Enter, and I get, oh, that looks like it's 17,576,000. So 17,500 and I think it was 26,000. If not, it's close enough. Right? So obviously there's more. We went from 100,000 to 17.5 million. So to find the difference, right? It says how many more. We're going to subtract the 2, leaving me with approximately, I'm just going to say about 17.4 million more, which works a lot better when we have a lot more cars on the roads nowadays. So, and actually in Oregon now there's more license plates and more different combinations. Right. New word probably for most of you is permutation, and that's an arrangement of items in a particular order. And the key things here is particular order, right? So order, we care about who's going to be the first one, the second one, and the third one. So example here is we have the order of 3 people, okay? And let's just, for my drawing's sake, we'll say that they're 3 different heights. So I can have a short, medium, and a tall. Right? That's one order. So let's see how. Oh, they're all together. So that's one order. Another one is I could still have the short person first, followed by the tall, and then the medium, and so on until all the different options are counted out. So that's an example of permutation. Factorial is the operation of multiplying numbers starting at the given number and multiplying all lower numbers. Okay. Now this is probably a new operation. It's an operation just like addition, subtraction, and multiplication. It's just something new. So here we have 5 factorial. That's what the exclamation mark means, is factorial. That means we're going to start at 5, multiply by numbers lower than 5. So we have 5, then 4, then 3, then 2, then 1. All those together makes 920. Okay. 4 factorial, just like 5 factorial, we'll start with 4 and multiply by the lower numbers, which, if we do that, is 24. And then 10 factorial, so you're going to start at 10, then to 9, then to 8, then to 7, then to 6, then to 5, then to 4, then to 3, then to 2, then to 1. That's a lot of multiplication there, and I don't think I want to do that in my head. And in fact, it was kind of a pain just writing it out. So in those cases, it would be nice to use our calculator, which our calculators do have a factorial button on them. So I'm going to hit 10 right there, and then the factorial is located right here, and we hit the exclamation mark and enter. And that's how we do factorial. All right, so that gives us that's 3,628,800. Right? So that's a really big number, and these numbers grow pretty fastly. Okay. Problem 2 in your books is how many ways can you file 12 folders, one after another, in a drawer? Well, we could do this a couple ways. Let's first do it with the fundamental counting theorem, which says that we're going to multiply all of our options together. So the first option in the drawer, we can choose from all 12 folders. So 12 is going to go first because we have 12 options. Fundamental counting theorem says we're going to multiply. And the next one is, how many options do we have in the next spot? Well, if we filed 1 already, we're down to 11. The third place is after we file 11, we need to file one of the last 10, right? And so on and so on. And if you notice, this is looking exactly like a factorial problem. Right? So instead of writing it all out and stuff, if we realize that's a factorial problem, we can just go straight to our calculator. And I can say 12 factorial, enter, and that gives me my answer, which is huge. I would not want to do that with pen and paper. Looks like 479 million. So there's 479 million different ways to file those 12 folders. Now you wouldn't think it because of, you can hold 12 folders in your hand, but there's very, very many ways to file them. All right. Now this one's going to ask you, what if in the last example we were only going to file 4 of the 12 folders? So 8 of them we're going to throw away. We're only going to keep 4. And how would this change our answer? Well, I don't think it would still be the 400 million answer. So let's look. This is the way we did it before, but now we're only filing 4 of them. So what we're going to do is we're only going to take the first 4 answers. Right? So we're only filing 4. After that, we're not going to file these last 8. So we can cross those off, and all we need to do is 12 times 11 times 10 times 9, right? Which is a little bit easier. I could do that, I think. See, we have 132 times 10 times 9. So this would be times 9 is 0, 18, 9 times 3 is 27, so that's a 28, and 11, so it went from, was it 400 million and something to 11,000, almost 12,000, right? So that cut it down quite a bit. But it'd be nice if there was a way that we could do this without doing it by hand like this. It was really nice when we could do the whole thing together as the factorial, right? This whole thing together as a factorial. It was nice when we could do that with some type of operation. Well, This is called the permutation, right? We said order does matter, so it matters which file I put in first, matters which one I put in second, third, and fourth. And these permutations are nice because of they can be written as 2p4. This means we have 12 options. We're going to permute 4 of them. Now, the most common way to say this is 12 pick 4, right? We're going to pick 4 of them, so it's 12 pick 4. The actual math that goes into it happens over here. All right, so it's n factorial, which stands for the big number, so that'd be 12 factorial in our example, over parentheses n minus r factorial, so it'd be over 12 minus 4 factorial. All right? Well, that's better. I think this is better than doing it by hand up here. But there's even a better way to do that. And let's go back to our calculators. And we do have some of these options, okay? So now what I'm going to do is I'm going to go 12. I believe we have to hit the 12 first. 12, and then is it this one? No, not that one. Escape out of that. Let's delete that. No. Okay. Down here, no, it's not there. So let's delete that. Well, where? Well, I'm having trouble remembering where it's at and everything like that. Where the actual button's at. It's been a full year since I've taught this, so give me a second to find it on the calculator and then I'll show you. Okay, I remember now. So we have 12, and then we need to go to menu, right? Menu, and this chapter is called probability, right? So it makes sense that we're going to be down at number 5, probability. And right here is that word permutations that we had. Oh, let me back up. I had some stuff in there. So permutation. So we're going to go to menu, probability, permutations. I'm going to put in 12 first, and then I'm going to put in a comma, which is located down here by the O button, 12, comma 4. That's going to tell it 12 pick 4. Enter, and it gives us 1188, which is what we ended up figuring out by ourselves. All right, so that's the permutation button. All right, moving forward, problem 3, 10 students are in a race. First, second, and third places will win medals. And how many ways can runners finish first, second, and third? All right, this is a permutation because the order does matter, just like the problems we have been doing. So there's 10 runners, so we need to write this out first. So let's first write it. It's a permutation problem. And we're going to have 10, and we need to pick 3 for medals. Okay? Now, I know it sounds kind of weird to say pick, but that's the notation that we use. So 10, pick 3. Now let's go back to the calculator, and let's figure out what this is going to be. So we have to go to menu, probability, permutations, and it's going to be 10, comma 3. Enter, and that's 720. There's 720 different ways for them to finish first, second, and third. So 720. Right. Good. So with that, you guys will be doing the first half of the homework assignment, right? Which is on page 678, 9 through 29 odd, and then 56 through 68. Right? Thank you, and have fun.